This lecture is about the USDA, or the United States Department of Agriculture. And instead of a PowerPoint file, there is a PDF slideshow. And this is something I got a while back from the USDA. And the US Department of Agriculture is the largest civilian employer on planet Earth. And it has a lot of different groups. The AMS, or Agricultural Marketing Service, Rural Development, Agricultural Research Service, and on and on. This is actually about the Agricultural Research Service, and it gives a good introduction about some of the things that are done in the area of agricultural research in food processing. And it's related to this class. Most of the ARS, or Agricultural Research Service, activities that I've been aware of over the years are about diseases and insects and field production related issues. This one is specifically, or this piece of information is specifically about things that are going on in the fresh and fresh cut produce area of research. So there is a facility near Berkeley in a place called Albany, which is very near Berkeley on the San Francisco East Bay area. And there's another one in Riverside. There's a lot of the food safety research that goes on at those two facilities. There's also one in Pennsylvania, and the main headquarters, the USDA Central, is in Beltsville, Maryland, which is right outside of Washington, D.C., and you might expect a cabinet level office like the United States Department of Agriculture would probably want its main headquarters near the president's office, since the director, the head of the USDA, is one of the cabinet members of the president. So it goes into some detail here. I am not going to check the names and phone numbers and email addresses on this, and I wouldn't trust them if I were you either, because people move and go to do their own things in life, and so people move and change. So always double check if you are interested in looking at some of this. But at the Eastern Regional Research Center, there is a major project on the intervention technologies for enhancing the safety and security of fresh and minimally processed produce and solid plant derived foods. So this is all about what can we do to enhance the safety of these foods that are not going to be sold directly out of harvest with nothing more than maybe some trimming, packaging, maybe some rinsing. But you buy apples in bulk, or a head of lettuce in bulk in the produce section of the supermarket, that's one thing. If it's being chopped up, bagged as ready to eat, it's being canned, it's being put into any value added product, it changes the issues and the concerns for food safety. Now, this is about fresh food safety. So we're not talking canned here. We're talking about fresh salads, sliced fruits, things of that sort. Their goal is to develop new or improved intervention technologies for eliminating or significantly reducing contamination by human pathogens, while maintaining quality of fresh and minimally processed produce and solid plant-derived foods. Pretty straightforward. So what kinds of things? You definitely want to spend some time, maybe save this file to your computer for study, print screen, pause this, whatever. You should know this list. These are some of the things that can and have been done and are looked at for other ways to optimize them for efficacy. Heat, pretty obvious. Use hot temperatures to kill pathogens. Grass compounds. So there are things like niacin and organic acids that are generally recognized as safe. You need to know that acronym. Generally recognized as safe. And these are things that had been used for many, many decades, if not many, many generations of human use before the kinds of food safety and product food adulteration laws and regulations came into being. So, and this goes back way long ago for the GRAS list. So certain things were considered to be safe, period. And there was plenty of history to just accept them as safe without forcing the same kinds of regulatory procedures and evidence, data collection to prove that things are safe that we've been using for generations. So the GRAS list, or generally recognized as safe list, includes food additives for flavor, cooking qualities, stabilizing the product, all sorts of reasons. But these particular ones are about food safety, keeping it fresh and free of pathogens, diseases. Chlorine dioxide gas or gaseous ozone with peroxyacetic acid. So this is a combination. Instead of using chlorine in a bleach type of a situation, liquid chlorine, which is sodium hypochlorite solution, bleach, which is also used in food safety, but instead of that, using chlorine dioxide gas. Very effective, very interesting results. It can be used in certain applications very well. Low dose irradiation alone or low dose irradiation in combination with other treatments, sometimes doing two things where neither one of them works really well on its own. You put them together as a 1-2 punch and they are highly effective. Now, irradiation is when you use some sort of electromagnetic radiation to sterilize or partially sterilize a particular product. Now, irradiation is something that has a bad name because we think of nuclear weapons and we think of nuclear reactors that have gone bad and radiated the environment. And there are radioactive substances that are quite dangerous. And even some of the stuff that is used in some food processing can be dangerous at the time of irradiation. Think of it this way. If I go in to get an x-ray, is that dangerous? Not anymore, not if you get one small x-ray, but if I get hundreds of x-rays, it can be quite dangerous. Let's say I got a massive overdose with an x-ray. Is that dangerous to me? Of course it is. Now I go home. Is it dangerous to my family? Not at all. I have been irradiated. I am not radioactive. I don't have any of the problems anymore, other than what damage it may have done to my cells. I can't contaminate anything else. I can't irradiate anything else. I am not radioactive. I was just exposed to an x-ray. It's exactly the same concept with irradiated foods. We are not putting anything into the food. We are only exposing it to some sort of high energy. Usually it's some sort of photons, and photons are exactly the same thing that come out of a light the incandescent or fluorescent lights that light your room, those are photons. They are modest energy photons. If they're lower energy, maybe that's what you listen to in your car. If you listen to AM or FM radio, those are just low energy photons. What if I make them really high energy photons? They're still photons, the same exact thing is coming out of your light, except they're high energy. So now they're X-rays or gamma rays. Our X-rays and gamma rays are UV light that gives you sunburn and cancer. Are they dangerous if you put them on your body? If you expose yourself to these things? Yeah. But if I get a sunburn, I don't come home and I'm not dangerous to my family. And so we irradiate foods, and the only time it's dangerous is in the irradiation chamber. You don't want people in the irradiation chamber, because what is irradiation trying to do? It's trying to break up proteins and DNA and other things inside of the cells to make that cell dysfunctional, so it no longer can either live or reproduce. And so if it's bacteria or fungi or some pathogen that could be a problem, you're essentially taking that cell, that bacteria that's on your food, and you're neutralizing it. Maybe you kill it, maybe you don't. Maybe you just damage it to the point where it no longer can effectively reproduce. Therefore, it's no longer a threat. So irradiation is not the danger people think of. It is perfectly safe. Irradiated foods can be fabulous. There are some problems with irradiation. It's not a perfect solution for all food safety issues. If it's so perfect, why don't we do it on everything? Well, it does alter things. It does break proteins and break DNA under these high energy pulses of irradiation. And when that happens, it can change the product a little. And people think, oh, well, that's what's dangerous. No, it's not dangerous. The same exact kinds of processes happen when you heat something up. When I boil it, or put it in a hot water bath, or I put it in an oven or anything else, cooking also changes things. And cooking heat, the very first thing, can be a great way to kill pathogens. But it also can cause undesirable effects where it no longer has the taste and texture and shelf life qualities that we want in our fresh food. So irradiation can be great in the right application, but it's not a magic bullet that solves these food safety problems for all. So what are they doing? They're trying to do low dose irradiation. So it doesn't damage some of the fresh food qualities that we want. It won't kill everything, but it will weaken them a bit when we give the second punch with some other treatment. Vacuum, steam, vacuum. This puts extreme pressure on cells. The vacuum creates a low pressure, creating a vacuum on the system with the food product in that you're trying to sanitize. And then you inject a bunch of steam in that vacuum. And what ends up happening is the superheated water, the steam, is going to be taken in very quickly by cells on the surface, the bacteria and fungi you're trying to kill. And it will severely damage or kill them. And then you pull a vacuum again. Very quickly you go through this process, and you can kill the pathogen with much less heat. And when I say heat, heat and temperature aren't the same thing. The steam is very hot, but there's very little of it. And so it doesn't heat up the rest of the product. It's only surface sterilized, and it's only the surface cells that get impacted by this. It can be very, very effective. Ultrasound using high intensity sonic sound waves can actually disrupt or break cells and damage them. So we can put our food through these ultrasound chambers that can kill certain bacteria. Competitive exclusion or biofilms. Fabulous, fabulous area of material science research where we use special types of plastics or other materials that, in combination with certain known designs or chemistries that prevent the production of these pathogens. Lots of examples of these kinds of films that have been researched and shown to be effective in reducing the spread of pathogens. One interesting thing here, I haven't seen anything on this in years, but there was somebody who had made the observation that bacteria has a really hard time growing and can't grow colonies on shark skin. Why? And it was determined that there's something about the shape, the design of the roughness of the skin that breaks up the ability of colonies to form. So you can only get these little microscopic colonies that don't go anywhere. And so somebody did some research to reproduce that texture on plastic. Now, would the plastic all of a sudden become a biological structure that prevented the growth of bacteria? Early indications were absolutely yes. I saw some preliminary research that just by changing the texture of the plastic to resemble shark skin at a microscopic level prevented significant growth of bacteria. Pretty amazing stuff. I would love if one of you decided to do your research project on this. If it sounds interesting, you already picked something else, you can change your topic, just let me know. But I'd love to read about what's happened over the last years. If there's anything, I don't know if it was a dead end, but it was a pretty cool article when they were talking about the original research and lots of other packaging materials. I'm going to take a quick break.